you will have some of this covered during the online portion of your course as well. So first off, atom. Yeah, what's up, Doug? Chapter 2. This is chapter 2 in the book. The atom, once again, you guys should all know this, right? It's the smallest matter unit of chemical elements. And so what happens is that it consists of a nucleus, which you see at the very core here, in the middle here. And within the nucleus, it has both positive charged protons, and this will determine the actual atomic number for the atom, and it will make each atom distinct from each other by the number of protons that they have. So it has an atomic mass of 1, which comes into play when we're talking about the mass number. The neutron is a neutral charge particle within the atom's nucleus as well, and so it has no particular charge to it. And once again, it has also 1 atomic mass unit, so they weigh the same. And finally, we have an electron that circulates the nucleus around it. Okay, and the nucleus, the electron is negatively charged, and that kind of makes sense, right? So, how many electrons will you have if you have 4 protons? You'll have 4 electrons as well. Very good. To try to balance the charges out. Does that make sense? If there's 4 positive protons in here, there has to be 4 negative electrons around it to balance it out. And so it orbits the nucleus, and it doesn't have that much weight to it, so it's usually negligible. The electrons is very important because it does share with neighboring atoms to form bonds, and we'll talk more about these chemical bonds in a second. So some definitions I want you to know is the atomic number. And the atomic number is shown over here on the upper left-hand corner of each element here. And so if you look at, let's say, aluminum here, it has 13. So what does that tell you then if it has the number 13? 13 protons. Okay, so it shows you how many protons there are, and it's their elemental number. Atomic number. And so over here, if we look at 10, it's 50. So you have 50 protons. How many electrons will you have? 50 as well to neutralize the charge of the atom. Very good. Okay, so each one is unique for each atom here. The mass number is which 2 items has atomic weight to it, or atomic mass units? Protons and neutrons. So all you have to do is add up the amount of protons and neutrons. So that will give you the mass number. So over here, the mass numbers you can see on the upper right-hand corner of all the atoms here, or elements within the periodic table. So oxygen here, if you look at it, it says 15.99999. So if it says 15.9999 and it has an atomic number of 8, how many protons are there? Protons? 8, right? Because the atomic number is 8. Yeah? It's the mass number. Okay, yeah, what's the mass number? Yeah, 16, if we round up. Okay, so we know the number of protons. How many neutrons are there?
8.
Also 8. How did you get that number? Say again? Yeah, it's neutrons. Not necessarily has to be the same amount as protons. You subtract the mass number by the protons. I don't have I'll write it over here. No, it's okay. So let's go back to that example here. So we have over here, it's 16. The mass number is 16. Over here, the atomic number is 8. So oxygen has how many protons? 8 protons. How many electrons? 8 electrons. Okay. How many neutrons now? Which, it's also 8 as well. And how do we get that? Well, we look at the mass number, right? The mass number here is 16, right? And remember, the mass number is the amount of protons and neutrons together. And we know that there's 8 protons here, so minus 8. So we have 8 left. So this is the 8 neutrons. Okay, I'll give another example. How about chromium here? It has 24 as its atomic number and around 52 for its mass number. So, how many protons are there? 24 protons, very good. Okay, so how many electrons are there? 24 as well. How about how many neutrons now? So 52 minus 24 equals 28. Very good. Neutrons. Does that make sense for everyone? If not, come to me and we could go on for more of this. Okay, so when we're talking about the electrons shells on the outside, the most energy is on the outermost shell of the electrons for the electrons. So potentially something like sodium and chloride. Sodium has just one electron on its outermost shell, while chloride has 7 of them. And to fulfill the requirement of its outermost shell, it depends on how many electrons there is. Some, like the first shell has 2 electron maximum, and then the second shell has 8, and then the third one also has 8. But so what I'm trying to get at is that here for the chloride we have 7 on the outermost shell. So it needs one more to fulfill that and be happy, basically. For the sodium, it has one extra one. So it could donate that extra electron to the chloride here to fulfill that. So what will the charge be after it donates the electron for the sodium? If it donates an electron to chloride, it will be positive or negative or neutral. If it donates the electron, okay, normally by itself, okay, if it has its own electrons, it should be no. No. It should be neutral if it's by itself, right? It's neutral, right? The amount of protons will be the same amount as electrons there are. Yes, once it loses that electron, then it's positive, correct. Good. If that's what you were thinking, great. That's perfect. Okay, how about chloride? It's gaining an electron, so therefore it's going to be negatively charged. Very good. Okay, and so once you have that, now we have ions. Okay, we have a positively charged ion and a negatively charged ion. Positive charged sodium ion and negatively charged chloride ion. Okay, so far it kind of makes sense? Okay, it's just to fulfill the outermost shell. Notice how this is now complete, and it doesn't have that extra one rotating around it anymore. Okay. So, positively charged ions are called cations. And so one way of remembering this, my professor told me this, is that if you look at cations, you want to think of it as being positive. Okay, so so the cations I want you to know is the hydrogen ion, the sodium ion, like that's displayed here, potassium ion, and so potassium you'll notice, and also sodium, they have different type of abbreviations for what they are. It's from their Latin or Greek word for them. Ferrous ion, magnesium ion. Magnesium, I don't want you to really know as much, but I want you to definitely know the others, and calcium as well. Not only know the abbreviations for them, but also know like their charges as well. So mostly all of them, the top three here are just singly one positive, while the ones on the bottom here are two positively charged ions.
Wait, so the first three are one positive and the last three are two?
Yeah, yeah. Yeah, anion is the negatively charged. So after an electron gets donated to that particular atom, it'll have this negative charge. So the only one that you'll need to know for this class is a chloride ion. So simple enough. The reason why I want you guys to know this is because it does play a key role into later things that we'll learn later on as well. So I want you guys to know it now so that you don't have to learn it later, or it will become easier for you to learn it later. Okay, so we just talked about how these electrons circulate the atoms, and so when you have the electrons interacting with other atoms, they form molecules, and molecules are formed when you have more than one atom together. And this chemical bond holds them together. And we have different type of chemical bonds that we'll talk about. First one is the covalent bond. And this is when they actually share their electrons with each other. So it'll be rotating around both atoms. So here they're all sharing it together. And you'll notice how some has a single bond, as this hydrogen gas is shown here. But this oxygen gas, how many bonds do they share? 2. So it's going to be called a double bond. Here we have methane, and it only has single bonds that are shared with the carbon there. Okay. Some have unequal sharing, and these are when you have a polar bond, polar covalent bond. An example of this is water, which I don't have here, but water is hydrogen with oxygen, and the hydrogen tends to be slightly positive. This is a Greek symbol. I forgot, it's delta? I don't remember. But it's delta positive, and then here is slightly negative here. So the hydrogen tends to be slightly positive, while the oxygen is slightly negative. It's not like a ionic bond where it actually donates the electron to the other atom. It's just that the electrons tends to hover around the oxygen more often. That's it. Since it's a little more electronegative. And then nonpolar things are covalent bonds are when they equally share with each other. So like this hydrogen, this oxygen, and this methane here equally share it. So these are nonpolar molecules. And the nonpolar covalent bonds are the strongest bonds of them all. So something to just take note of, that covalent bonds in general are the strongest one, nonpolar even more so. Okay, we already kind of talked about ions. So ionic bond, pretty simple, is when you have atom donating its outermost shell's electron to another atom, fulfilling their outermost shells. So here we have the sodium once again donating the electron to the chloride, and now we have the ions together, and they form a bond with each other. The hydrogen bond is slightly different from the rest. It is a weak bond, and this weak bond is due to that partial positive of the hydrogen within a water molecule. This is the water molecule here. So remember, is this partially what? Positive or negative? It's partially positive, correct. While the oxygen here is partially negative, correct. So this partially positive is going to be attracted to what side then of this water molecule? It's going to be attracted to its negative side, right? Yeah? Because this is the hydrogen side here is partially positive. It wants to attract to the partially negative side of this water molecule. Okay, how about this? It's going to be attracted to the negative, which is the oxygen side. Yeah, very good.
Thank you.
How about this oxygen here? It's going to be attracted to the positive, right? The hydrogens of these water molecules here. Very good. So this interaction here, this thing is the hydrogen bond. These dotted lines here are the hydrogen bonds. Okay. So what are these solid lines then? What kind of bond was that? Covalent bonds, very good, because they're actually sharing the electrons with each other. Okay, so we have covalent bonds with the oxygen and hydrogen within the water molecule itself. But if we're talking about these bonds, these hydrogen bonds that form, they're forming across two different water molecules. And these hydrogen bonds will form to any of these partial negative atoms here, so fluorine, oxygen, and nitrogen. But mostly we'll see it in water molecules like this. Van der Waals forces is yet another one. This is the weakest of them all. Okay, so hydrogen bonds are pretty weak, but Van der Waals forces are even weaker, and they're not really a bond per se. It's just this interaction or attraction between neutral atoms. So out of all of this here, you'll notice that here there's no polarity to any of this here. So this molecule here versus this molecule here is going to be sharing this Van der Waals forces together, and same thing as over here. And you'll notice that since there's charges over here, what kind of bond will that be if there's charges? If there's actually, so they're actually donating, it's not partial charges. Is that actually charge? A positive, a cation, and an anion? So it will be what kind of bond? It has the word already inside the ionic bonds. Very good. And over here, you have oxygen with a hydrogen of another part of this molecule. So it's going to form that hydrogen bond. Covalent bonds are between this carbon and this oxygen, this double bond that you see here. And even over here, this disulfide bond as well. So try to be able to recognize or see these different types of bonds and know which one's the strongest, which one's the weakest. Talking about Van der Waals forces, so the gecko, when they grip onto things, they utilize this Van der Waals forces to be able to maintain that grip. So that's kind of interesting. Okay, water. Water is, what's its chemical formula? H2O, very good. There's two hydrogens and an oxygen. It's very essential to life. It has different properties that you want to know. One is surface tension. And what surface tension is because of that hydrogen bonds that form between water molecules, they'll be able to have this surface tension that is formed due to the cohesion between these molecules, water molecules. And that's why, what was this insect again? Water strider. Remember from the Royal Seiko? We saw a couple of these. They're able to, due to the surface tension of the water, they're able to actually stride on water. Also, we also talked about this in the ecology section where it helps moderate temperatures, right? Whenever it's a hot day, people tend to flock to the beach, right? Due to the absorption of the heat or temperature, and so then if it absorbs the heat due to the hydrogen bonding of water, and tends to retain heat as well. So if it starts to cool off on land during winter time, it's still mildly comfortable towards the beaches because they tend to still retain the heat due to the reforming of the hydrogen bonding. And we also know that during perspiration, it evaporates, and that evaporation helps us cool down for our body temperature to cool down. So that's how it will moderate temperature. It helps absorb heat due to the hydrogen bond and retains heat as well by reforming those bonds, and evaporates to help us cool down our bodies. Oops, let me take that off. And another property is that we all know that ice floats, and ice floats due to the hydrogen bonds. And if you look at the hydrogen bonds in the liquid, notice how the liquid, are they closer or further apart? They're closer, right? Compared to when it's actually frozen. Frozen-wise, the water molecules between each other tends to be further apart. So which one's going to be more denser? Which water? The liquid form or the solid form? The liquid form is more denser, correct. So that's why it tends to sink while ice tends to float. Okay. This helps us, for water animals to be able to live in icy conditions. If ice was denser than the liquid form of water, then it's going to fill up the entire sea. It just kills off the animals. But since it's forming only on the top portions of it, life can continue under it. Water is also a solvent. What a solvent is, it's just the liquid portion of a solution. When you have something like solute here, over here in the bottom right, is this is salt. Okay, so this is solute. These are the solids that dissolve inside the solvent to form a solution. So when you fill it up with water, it dissolves and then it becomes a solution. So salt water solution in this particular case. So some of these are definitions that you'll need to know, like solutes and solvents, and when they're mixed together, it will become a solution. Okay, so within some solutions, you'll see that some things are hydrophilic versus hydrophobic. If you dissect the words out, hydro meaning what? Water. Philic? Anybody know? Yeah, attracted to, philia, attraction or liking. Yeah, so this, whatever it is, it's water liking. Okay, so these are substances that ends up wanting to interact with water. So we have this chloride ion here, and the chloride ion is what kind of charge? It's negatively charged. It's an anion, yes, but it's negatively charged. And so it's going to attract what side of the water molecule then? Okay, which are the hydrogens. Right, very good. So as you can see, the hydrogen portions are surrounding the chloride ion. How about the sodium ion? It's positive, so it's going to attract the negative side, which the oxygen side of the water. Very good. So and we know that when we put salt in water, it dissolves, and because of the ionic properties are hydrophilic. Hydrophobic substances, on the other hand, are nonpolar molecules, and these nonpolar molecules make it. What does phobic mean? Fear, afraid of it, yeah. And so they tend to not mix with water, and so they don't dissolve in water. They actually repel against it. Yeah, like oil. Very good. And we kind of talked about acids and bases before in our ecology section, but just to reiterate some of it. So acids, these are molecules that end up releasing hydrogen ions. And so anything that's below pH of 7 is called acid. And base, on the other hand, is everything that's above the pH 7. It's also called alkali as well. And these are molecules that end up taking in hydrogen ions. So everything over here. So at 7, pH 7 itself, that's when it's neutral. Okay, so pH 7 is neutral. Oops, sorry. pH 7 is neutral, sorry. Equals neutral. And what's neutral? It's water. Water is neutral. pH scale goes from 0 to 14. 0 through 14. So 0 being what? The most acidic, while 14 being the most basic or alkalytic. Yeah, alkaline. The thing about the pH scale is it has this equation. You don't have to memorize this equation, but I want you to understand what this equation is talking about. Logarithmic scale is that every single number is a power, it's 10 times the amount of the previous number. So if you have something that's pH 2, how much more acidic is it if it's pH 1? 10 times. Very good. If something is pH 5, how much more acidic is it if it's pH 3? From 5 to 4, it's 10 times. From 4 to 3, it's 10 times again. So 100 times. Got it? Yeah? Okay, I'm going to make it a little trickier. Let's see how okay, so pH 5 is how much more basic compared to pH 4? It's like say again? It's how much more basic is pH 5 to pH 4? Is pH 5 more basic than 4? pH 4? Yes. Okay, so how much more basic is it? 10 times. Okay, not negative 10. Does that make sense? Okay, so how much more basic is pH 6 compared to pH 4? 100 times. Very good. How about from How much more acidic is pH 10 compared to pH 12? 100 times as well. Okay, let's do one more. How many times is it from pH 12 to pH 3? How much acidic is pH 3 compared to 12? So 10 to the yeah, very good. 10 to the ninth. So you have 9 zeros. So that's a billion. Yeah, a billion times more acidic. Okay. The other term I want you to know is buffers. Buffers in general help prevent pH changes. So our blood actually has a buffer in it. Our blood's pH is around 7.4, which I want you to know. And so if we somehow inject ourselves with something slightly more acidic or something like that, it's going to still remain relatively around 7.4. Unless you end up injecting a lot of amounts of very acidic or very basic solution, then it's going to fluctuate. Okay, but if it's not big amounts and it's somewhere near 7.4, it's going to stay at 7.4, even though it is something like if I'm injecting urine into my blood, which is pH 6. Okay, it's still going to remain relatively close to 7.4. It might go down to 7.3-ish, but it's going to remain near 7.4, even though we're injecting a pH 6 liquid. I arbitrarily chose that. I didn't do it on purpose. So here's a question. Put the following solutions from strongest to weakest base. So do it by yourself right now to see. I'm going to pause it for a sec. Okay, so which one's the strongest base? Ammonia, very good. So this is number 1. Next strongest? Bleach, number 2. Very good. Human blood is next because it's what pH? 7.4, very good. And then saliva's next, 4. And then apple juice at 5. Good. Alright, so we're done.